Stoke's theorem. So I want to do a numerical model of Stoke's theorem. So let me tell you what Stoke's theorem says. And then I'm going to show you how I'm going to do this. And I'm going to use Monte Carlo to calculate the flux. Let's just get into it, because I got a lot of stuff to do here, and we better get started, or we're never going to finish. So first of all, Stoke's theorem gives a relationship between a path integral for some vector function f. I just picked the vector function f. So this is a path integral around a closed path, and it would be equal to a surface integral over any surface bounded by that path, where you take the curl of that same vector field, and this is the flux of the curl. Okay, so right there's a lot of stuff. I'm not deriving Stoke's theorem. Okay, we're just going to use it. In many cases, you would use Stoke's theorem to either evaluate a surface integral as a line integral, because this is easier, or the other way around. But I'm going to do it both ways. I'm going to do both of these numerically. And I've already done a couple line integrals. Line integrals are not too difficult. They're actually pretty easy in Python to break it into small pieces. This is the hard part. Okay, so let's first just take the curl of this. So I'm going to pick a force. I picked this force y negative xz. I want something that is, usable. This is an example that actually in a lot of cases you could do this analytically. But again, I think doing it in Python gives some illustration into the way the whole thing works. So the del operator is just the partial with respect to x, partial with respect to y, partial with respect to z. So if I want to find the curl of f, one way to do that, and my surface is this. I'm going to tell you this is my surface. I'm going to start right here and go along this curved circle in the xy plane, and then go along a curved circle in the yz plane, and then in the zx plane, and then I'm going to find the surface bounded by that. Okay. So the curl of f, we need that. The best way to do this, the easiest way, is to find the determinant of this x hat, y hat, z hat, then the del operator, partial with respect to x, partial with respect to y, partial with respect to z, and then the components of my vector, y negative x, z. So if I do that, if I do expand about the x direction, then I get the partial of z with respect to y, which is 0, minus the partial of negative x with respect to z, which is 0, so I get 0. If I do it for y, I get the negatives. It's going to be a negative, so I get the partial of y with respect to z, 0, minus the partial of z with respect to x, 0. And then I do the z direction. I get the partial of negative x with respect to x is negative 1, minus the partial of y with respect to y, which is 1. So I get the curl, in this case, is just a constant 0, 0, negative 2. But the method, I picked a function just because I wanted something that was I had seen before. But the method I'm doing it, the great thing is that it works for any function. I mean, you do have to actually take the curl of this product right here. I didn't do a numerical curl, which I'm even thinking would be kind of difficult to do. Probably could do it. But actually now I want to do that. I want to make a numerical curl function. But anyway, so there's my numerical curl. What I'm going to do for this part right here, I'm going to do this side first, and then we'll come back into this side. So here is the surface over which I want to calculate the flux. So I have this function, which would just be a constant vector, right? That's my del cross f. Is just that constant. Oh, it's actually going down. Constant downward vector. But if I want to find the flux, del cross n hat is a vector. If I break this into little pieces, n hat is going to be in different directions. So I could get a mathematical expression for that n hat. Not too difficult. I could get a Python expression for n hat very easily. But the problem is, how do I break this into tiny squares? Okay, imagine that I just make a little square right here, and I put that on the surface, and then I add up going this way. Go across. That seems fine. But the next row, if I have the same size square, is not going to have the same number of pieces going across. And it's kind of, I mean, you can make it work. But breaking this into squares is not easy. You could break this into spherical pieces, but then again, it's not as fun numerically. I like to do things that are computationally easy to set up and conceptually easy to understand. So since it's hard to figure out how to actually add up all these things fairly, I'm not going to. Instead, I'm going to use Monte Carlo. So the Monte Carlo method says I'm going to just make a whole bunch of actually circles over here, randomly distributed. And for each one, I can calculate n hat. And it'll have an area dA. So if I have that one little bitty circle right there, and I have n hat is that way, has a size dA, and then my vector is, here's my del cross f, then I can say the flux, I'll call this whole side equal to the flux. I'll use phi. And I'll call this side equal to the work. I'm just making up stuff here just so I can call it. Then the flux just through that one part, I can assume the this is constant, which it is over that, but I could say d flux is just going to be del cross f dot n hat dA. And I can calculate it for that piece. And then I can do it for all the other pieces, even though they have different directions. And I want to make these circles, let's say I break this into 10 circles. So n equals 10. I'm going to randomly put 10 circles in here. I can calculate the r hat, right? So let's say I have, here's a circle from the side right there. I can find the vector location r of that. Then the unit vector n hat is just going to be the unit vector for r. It's in the same direction if I have this thing centered on the origin. So that's pretty easy. What about the area? Well, if I want to, I can find the area of each little circle by using, I want the area of all my circles to add up to the area of this piece. So this is an eighth of a sphere. So I'm going to say dA is going to be the area of that piece, which is 4 pi r squared, that's radius r, divided by 8. And then I want to divide that by the number of pieces I break it into. That way when I add up all the pieces, at least the area is constant. Now they won't be completely evenly distributed, right? Because it's a random process. But it should be close enough to give a good answer. I know there's a lot to process right there. But that's what we're going to do. So let's start off. I'm going to focus on calculating the flux. I already have my vector force right here. The first thing I want to do is just make a whole bunch of disks in the shape of this. So here's how I do that. Let me get another piece of paper. So in Python, in GlowScript v Python, we have the function random. Random. Parentheses. It returns a number between 0 to 1. So I can generate a point in space with random, random, random. And it will be a vector, let's say r equals 0.1, 0.77, 0.88, whatever. Okay. And if I generate a whole bunch of those things, it would fill up a cube that's 1 by 1 by 1. Those would be all it'd be in that space. And that's not what I want. So what I want to do is to generate all these values and only accept them if they lie in this shell. And so I have to give this shell some thickness. Let's call that dr. So if the magnitude of this is between r plus dr and r, no, that'd be the other way around, and r minus dr, then I'll take it. Otherwise, I'm just going to throw it away. And then that should help me build up my space like that. Okay, so I'm going to generate all those cubes, but I'm only going to accept the ones that fit in that tiny little shell. Okay, so let's get started. We got a lot of work to do. It's going to be awesome. Okay. So let's start with this. I'm going to start with how many pieces do I want to break that into? I'm going to say let's just say 10. right? 10's a good number. Wait, did I switch over? No, I didn't. Good thing. Okay. I'm switched over. So here we have Python. And I'm going to give you the code for this. Okay, so don't worry. So I have n equals 10. Let me make that a little bit bigger. That's the number of pieces I'm going to start off with. And I can always put more pieces in there later. I'm going to say r equals 1. That's the radius of my thing. Now, I do need to pick this thickness of the shell. I'm going to say dr equals 0.001. I don't know why I picked that. Now I can pick dA. Like I said, dA is the size of each piece, which depends on the number of pieces I break it into. If I break it into 10 pieces, the size is going to be bigger than if I break it into 100 pieces. So this is going to be, I have 4 over 8, so that's a half. So I have 0.5 times pi times r squared divided by n, the number of pieces. Okay, so now let's start to make our pieces. So I'm going to say this. I want a counter. I need a counter. I'm going to say n equals 0. And let's just do this simply. While n is less than n, do the following. N equals, I'll print n. And then do n equals n plus 1. Just to show you how it works. Okay. So that printed out 0 to 9. I'm making sure I'm printing things right. I always like to do that because I'm always questioning my own choices in life. And I would like to test my choices. So what I want to do is to create a random variable vector. So I'm going to call this RT for temp. And it's going to be a vector R, the big R, right, times vector random, nothing in there, random, nothing in there, random. So that returns a number between 0 and 1. Let's just do that, and let's print out all these RTs just so you can see what's going on here. So this should print 10 random vectors. Each of the components should be between the value 0 and 1. Now, I don't want to keep all those, right? So how do I know if I keep them? Well, let's just say this. If the magnitude of RT is greater than R plus dr, no, R minus dr, and mag RT is less than R, oops, I messed it up, R plus dr, then I want to keep that. So if I want to keep that, let's just put a point there. So I'll just put a sphere, and the position of that sphere is going to be RT, and the radius of that sphere, let's put it at 0.01. Now also I want to count that one, right? So I'm going to put this n equals n plus 1 in my if statement. So I only increase n if it counts. So I should get 10 points, spheres, near the surface of the sphere. Let's see if this works. I should save this. Stoke's Theorem, Monte Carlo. Save. Run. And something happened. You can't find the variable sphere because I spelled it wrong. Okay, so this doesn't look like much. But I think it's legitimate, right? That's only 10 points, and they're spheres. Let's just increase this to 100 and see what happens. Okay, so now you can start seeing the shape of my eighth of a sphere. So I'm pretty happy. It looks like my distribution's working just fine. Okay, so let's put this back at 10. Now, I don't want a sphere, right? I actually want to put a little circle to represent that, and I want to orient the circle so that each one is pointing away from the sphere. So let's get rid of this, and let's just use a cylinder. A cylinder in Python has really 3 important properties. Number 1 is the position. That's the location of the one end of the cylinder. Axis is a vector from the one end of the cylinder to the other end of the cylinder, and then the radius is the thickness of the cylinder. So this cylinder is going to have a position equal to RT. The axis is going to, I want that to point away from the origin. So that's just going to be equal to norm RT. Norm is a unit vector RT, but I have a problem, and then that would return a unit vector of 1, and so that'd be a thickness of 1, and that would look a little weird. So let's just multiply that by dr times. So it would just be super thin. Now I need the radius. So if I want it to be legitimate, I could put anything I wanted to. But if I wanted the radius, that if I say it has an area of dA, so dA equals pi r squared. That's the actual area of the thing. So r would be the square root of dA over pi. So let's put the radius equals square root of dA, which I already have, divided by pi. Okay, so let's just see what that looks like. So there's my 10 disks. 1, 2, 3, 4. Some are overlapping. That's fine. Okay, let's increase this to 100 and see what it looks like. So that actually looks pretty good. So it doesn't completely cover the area that I want because there's a random process going on. But it's kind of close. And the overlapping hopefully will all wash out in the end. And of course, it's only 100. I could easily do 1,000. And you see there, that looks pretty good. That's kind of artistic too. If you wanted to, you could change the opacity of them to make them partially transparent. You could change the color. You could do all sorts of things, which I now want to do, but I want to also finish this. Okay. So I have my cylinders, and now I can actually calculate the flux through each one based on my force. But let's go ahead and make the force. So I'm going to say this, def F RR. So this is going to be a function that I give it a coordinate, x, y, z, and it returns the vector value for the field. So this is just going to be return, what did I say the force was? Where'd it go? There it is. I said it was y negative x. Yeah, y negative x. So this is going to be the y coordinate of RR, which is going to be vector RR dot y, RR dot minus RR dot x, RR dot z. Is that right? Yeah, y negative xz. Yeah, that returns that. Now I'm also need the curl of that function, right? So let's just, it's just a concept, but let's go ahead and call this def curl f of RR, and it's constant. So let's just return the vector 0, 0, negative 2, just like I said. Now I need one other thing. I need phi. Phi equals 0. I want to calculate the total flux, so I'm going to have to calculate the flux for each individual one and then add it to that. So I need to start with something. So I need to start with a flux of 0. So once I make my cylinder right there, I can go ahead and calculate the flux through that. Let's just say d phi is going to be equal to the dot product. And dot product is built into Python. So if I say dot vector A, vector B, it takes the dot product between them. So this is going to be dot curl f of RT. I want the curl of that, which is a constant value, but that's fine. And R hat, n hat. Curl of f dot n hat. Well, n hat is just going to be norm RT. Now that's the dot product. I need to also multiply that by dA. Remember, the Stokes theorem is the surface integral of curl of f dot n hat dA. I need that dA in there. So that's the flux of that one cylinder. Now I can add that flux to the total flux. Phi equals phi plus d phi, and that's that. Okay, so then once I'm done with that, I can get out of my loop and say print flux equals phi. And I'm going to leave off the units because I didn't really have units or anything else. And let's just see if this works. And it didn't. T dot. Again, it's a case where Rhett cannot type. What T dot? RT. I added that dot. Wait, what was the error? T dot is not a function. T dot E, T dot dot. What the heck? Where'd I have that? Oops. I just made a mistake. Okay, so it didn't even make, I think I must def curl RR vector. See, it's not even making all this stuff, but maybe it is. Radius dot curl RTF. What the, oh, let's try changing this to Python 3.0. Sometimes that makes a difference. Okay, that did. Okay. So I have a negative flux. That seems to be legitimate. Negative 1.59. And I could change the number of pieces I break that into. I could do whatever. So I could break this into 5,000 pieces, because if I can do it for 1,000, I can do it for 5,000, right? There's no difference. And I get about the same answer, so that's kind of cool. Okay, so now we need to do a line integral around the same path. So I want to start at one corner and move along that path. So I actually have 3 path integrals to do. So let's just start. Let me start this. So I'm going to use a ball. So ball equals sphere, and that's just going to be my marker, my location. I'm going to start this at vector R0, 0. Oh, position equals R0, 0. That's where I'm going to start. I'm going to start on the x-axis. The radius is going to be equal to, what did I use before? 0.04. 0.04. Color is yellow, just so we can see it. And then, this is important, make trail. So when it moves, I can actually see where it went. And let's just run that. So I'm going to move the ball along that path just so I can have a visual thing to look at. So there's my ball right there on the x-axis. So the first thing I'm going to do is I want to move this ball this way. Okay. Now, I need to do 2 things. I need to move the ball, which that's easy to do. I can just pick a parameter. I'm going to say theta, and I can just say the vector is r cosine theta sine theta 0, and then just increase theta. So let's just do that, and then let's just do that, and then I'll show you what we can do next. Okay, so down here, now I'm going to say theta equals 0. Okay, let's do this. In S, this is for the in. I need another in P for the path is going to be, let's just break it into 10 pieces. So now I can say d theta equals, how far is that going to be? I want to break that into 10 steps. So it's going to be pi over 2 divided by 10. So it's going to be pi divided by 2 times np. Now I can say while theta is less than or equal to pi over 2, that's where I want to end up, do the following. I already have the ball already there once. So let's go ahead and, I already made the ball once. So let's move the ball. So let's move theta. So I'm going to say theta equals theta plus d theta. Now I need to move the position of the ball. Ball.pos equals r times vector cosine theta sine theta 0. And I think that should move it. Let's do this. Rate 10. So this says only do 10 steps per second. And since I have 10 steps, it should take a second to move. And that'll give me time to move the camera around and we can hopefully see it. Okay, so there it is. It moved. Oh, it went a little bit too far. That's not a huge deal. Let's just do this. Let's move this down here. Or no, maybe I'll just put this less than. Not less than or equal to. I made an error. What did I do? Oh. Okay. Okay. Oh, it didn't go that far enough. I'll just put this at less than or equal to then. Fine. And that's only 10 steps. Those kind of problems don't really matter when you break it into 1,000 steps. Okay, that's good. Okay, so but now I need to find dr, and dr is a vector in the direction of the path. It has a length of the whole path divided by the number of steps. Let's go over to paper so I can write this down. Okay. So I knocked my light over right here. Switching to paper. Okay, let me get a new piece of paper. So here I have the XY plane. And then here I have the angle. I'm moving along this path. There's my ball. There's the angle theta. So this is cosine is the x direction, sine is the y direction. That's fine. But what about this vector dr? Well, I know I can find the magnitude of that. But what about the direction? So let's say this. R equals the vector r. No, r is going to be the vector r times cosine theta x hat plus sine theta y hat plus 0 z hat. So dr is the direction of change. So I can actually just take the derivative of that. Dr is going to be equal to r times the derivative of cosine theta with respect to theta is going to be, this is partial I guess, it's going to be negative sine theta. The derivative of sine theta is going to be cosine theta. And the derivative of 0 is 0. So that is my, if I want to, and then I want to divide that by the magnitude, if I divide this by r, this does have a magnitude 1, because this squared plus that squared is indeed 1. Okay, so, but I don't want dr to have a magnitude of 1. I want it to have a magnitude of the step size. So let's just say dr is going to be the vector negative sine theta cosine theta 0 times the total length, which is going to be 2 pi r divided by 4. So 0.5 pi times r, all of that divided by np. Is that right? Is that what I did before? dr, yeah. 2, yeah. Because that's the length of a quarter circle, and then divided by the number of subsizes. Then, and that's a vector. Then when I go to calculate the work, I can say the d work is just going to be f dot dr, work equals work plus d work. So I can do that through each step. Okay, so let's do that. And then how am I going to do that in the, what about this next move? So here's my next case. I'm going to go here. So in this case, I want to start over and set theta equal to 0. But in this second path, I'm going to say r is going to be equal to the vector, the x coordinate is going to be 0. The y coordinate is going to be the adjacent of that triangle, so cosine theta. And then the z component is going to be sine theta. And then when I take the derivative, dr is going to be 0 negative sine theta cosine theta, because I'm just taking the derivative of those. And then I have that same thing down here. This is path 2, 1. And now the last path, I'm going to go from here to there. And so now I'm going to let that be my theta. So for 3, r is going to be equal to the x coordinate is going to be sine theta. The y coordinate is 0. And the z coordinate is cosine theta. So dr is going to be, now take the derivatives, I get cosine theta, 0 negative sine theta. Okay, so I should be able to do that. Let's just do one step, one path, make sure it works, and then we'll do the other path. But let's switch back to the computer. There we are. Okay, so here we go. Okay, so I have this moving along that path. I do need to calculate the work. So let's say this, work equals 0. Now, in order to calculate the d work, I need this dr vector. So let's say, that's weird. dr equals, what did I just say? So let's say vector negative sine theta cosine theta 0 times 0.5 times pi times big R divided by NP. So however many pieces I break NP into. Now I can calculate. Do I want to calculate the work first and then? I think I need to calculate the work and then move the ball, because I have the ball already at one position, which is still already at 0. So I think actually it doesn't matter. Let's just do it after this. So let's say d work equals the dot product of f at ball.pos, right? Because that's the location of the where I want to find the thing, and dr. Yep. And then I'm going to say work equals work plus d work. And then I can print out the work, but it shouldn't really matter. It's not the full path. It's not the answer. Let me just print it just to make sure I'm getting a value. Okay, let's run that. Okay, so I'm getting a negative value. Cool. Okay, now I just need to redo this whole thing. So I'm going to copy this stuff. I don't want to print it. I need to copy all this stuff, and I need to do in the YZ plane. So let's go down here and do another loop. Now, before I get that loop, I need to reset theta equals 0, right? Because I'm starting over with my theta. It's going to be the same number of pieces, same rate. Now, dr is going to be, I'm looking at my notes right here. I said dr is 0 cosine theta negative sine theta. So I can delete this stuff. And, oops, there's a parenthesis right there. Yep. And the position is going to be equal to 0 cosine theta sine theta. So I just get rid of this other 0. Okay, so this should move in the second direction. Let's just see if it finishes the path correctly, ends up in the right spot. Okay, so you see where I went? I went up there and down there. Now I need one more path. So let's just copy this whole thing again. Copy all of that. And I reset theta equal to 0. Now, in this case, I'm looking at my notes. dr is sine theta. Let's copy it. Let's delete all this. dr is cosine theta. 0 negative sine theta. And then get rid of this. Wait. Cosine theta, 0 negative sine theta. Oh, that's right. That is dr. Cosine theta, 0 negative sine theta. And then r is going to be equal to sine theta, 0 cosine theta. Sine theta, 0 cosine theta. Okay. And then let's just, I'm not going to print out the work because I want to be a surprise. I just want to see if it completes the 3 paths. Okay, so then I love this, right? Because there you have your flux through this surface and then your path bounding it. I mean, it's pretty, right? That's pretty. And then I can zoom in through that and just do, that just looks good. Okay. So now I need to just go ahead and print out the whole work. Did I print the flux? And let's print, is that the last one? Print W equals W. And I'm not going to put the units because it's all fake stuff. Let's see, the moment of truth. Here we go. Oh, that didn't work. Something. It looks like I'm off by a factor of 2. Let me run it again. I mean, there's a randomness in there, but I think Huh. Okay. Well, let's see. While theta, so it's dr is the vector pi times r divided by np 0.5. Why am I off by a factor of 2? Let's do this. Let's just break np into 100 pieces. Maybe that's it. And then I'm going to make this go faster. Faster. Because 10 is not very many. Wait, 1, 2. Where's the third one? I don't have the third one. Oh, there it is. Ha. Whew. Okay, now let's run it. That could be the problem. Because 10 is not very many. And there it's moving around. It's going. That's just pretty cool right there. It's still too high. Maybe I have a problem with my flux. Let's see. Let's see. I don't think so. Why am I getting off? Okay, so my flux, I'm running it in another program right now just to, I did this earlier. Okay, and it's working for there. So I must be getting a problem with dr, see dw is f ball dr. What's my f? Maybe I had a problem with my f. F is r minus xr rz. That's fine. And then, so down here, this dr is vector. The first one is vector sine theta cosine theta 0 times, I had pi, I had it like this. Let's just see if this, I had this, it's the same thing. Times pi times r divided by 2 times that. It should be the same thing, right? It's the same thing. And then, oh, no. Ball.pos equals r times vector, okay. dw equals dot f ball dr. What the heck is going on? 2 times n pi r cosine theta dr. Oh, that's wrong right there. I'm really perplexed. Okay, I'm gonna get ready to copy my other code and just see if it works. It's embarrassing, really. You get all excited, you think you got everything, right? But no, you don't. NP is 100. Do that again. W equals W plus DW. The only thing I can think of is here I'm actually, in my other case, this may be it. I have DR, DW, and I actually put the ball, this must be it. Control X. Put this down here. Let's do that. Put it after I calculate the work. That must be it. That's got to be it. It's got to be it. It's got to be. Okay. It's going to work. It's got to be it. Ah, it didn't work. What am I doing wrong? Pi over 2. Okay, let's see. All right, I'm going to show you my other code. That's what I'm going to do. I got this to work in another code, and I made some errors somewhere. So let me just pull this over. Okay, so here's my other code. I did this in GlowScript. So I wasn't sure it would work. So I kind of did it beforehand, which I don't always do because I like to be a surprise even for me, but I want to make sure it actually works. So this code, I don't really need to go over everything. It's the same thing. There's some small little error in this. And I will give you a link to both of these codes, and maybe you can find it. But let me run this one. This So there I got the same flux. There's my thing going around in a circle. I have no idea what the problem is, but the idea is legit. It's legitimate. I don't know why it's taking so long, but it's going to get it. It's going to get it. And there, see, now I get negative 1.59, negative 1.61. So that agrees. That's good. Okay. Whew. So that's a lot to do. Now, I do want to do another example with this because the thing is, it does not matter what shape you have bounded by that curve. You can have any shape. And so I want to do two different shapes of the same curve. Not this curve. I'll just use a circle. But I'll do that in another video. So, sorry it took so long. Sorry about the error. But it was kind of fun for me and probably fun for you too. So that's that.